my project is an attempt at implementing an error-resilient JSCC scheme for image transmission over error-prone channels. So now, why do we need this? Well, the demand for wireless communication is increasing, and with that, the demand for image transmission over those wireless channels. Now, although current coding schemes and error tolerances are great, there is room for improvement, of course, and these schemes will need to be improved if future demands are to be met. So now I'd kind of like to take a moment to review some background information that the research paper doesn't include or glosses over. So the first topic is, what is JSCC? Well, non-JSCC coding schemes, like traditional coding schemes, they have kind of a separate source coding step followed by a channel coding step. And so the source coding step, its main responsibility is to reduce the redundancy in the bandwidth. It compresses the data, or in this case, the image. And then after that, the channel coding, it kind of preps and sets up the message to be sent over an error-prone channel by incorporating error tolerance. And so this, might take the form of adding redundancy or just kind of changing the scheme, as we'll see later on. So that's traditional coding mechanisms. JSCC kind of is like the joint of those two, kind of like merges, and there's not exactly separate coherent steps, or JSCC just refers to the joint of those two processes. And so the specific JSCC scheme that is used in the research paper looks as follows. And although there are several steps, we'll go into detail into each one before we present the results. And so the top row here is what happens at the transmitter. It's all the encoding. And then the bottom row is at the receiver, decoding. Now, just a few quick notes. This top left block, the first step and the last step, these are kind of standard steps in JPEG image compression and decompression. And also, these two rows, they look like mirror images, but they're not quite, just due to the complexity here. And this is because if an error occurs, the error will be detected at this stage in the receiver. And so then it kind of goes back and attempts to make modifications to the signal and then try again. And there's just kind of this cycle until the receiver does not detect any errors, and then it proceeds to decompress what it has. So going into detail, the first step, the DCT. Now, the DCT stands for discrete cosine transform. It is very similar to the discrete Fourier transform, the only difference being there's a cosine term instead of just the exponential. And a cosine is the sum of an exponential and its conjugate, so the DCT kind of might store more frequency components, if you will. Now, since we are specifically focusing on images, we're going to be using the 2D DCT, and the equation for that is shown here below. Now, after the DCT is taken, we perform quantization and zigzag scanning. So quantization, if you might recall, it's kind of shown up here. Basically, a number is taken, you divide it by a quantization coefficient, you round that to the nearest integer, and then you multiply it by that same quantization coefficient. And so what you end up having as a result is almost the same number that you had originally, rounded to the nearest multiple of that quantization coefficient. This is great for compressing images, and it's very commonly used. Now, since we're quantizing specifically images, we can try to exploit essentially human perception patterns. This is valuable to compress the image more, without actually losing valuable information. Because if we know that humans do not detect certain parts or certain components of an image, we can remove those, reduce the bandwidth, and not suffer any loss in quality. So two commonly exploited human perception patterns are shown below. The first one, higher frequency components are less distinguishable. Humans typically can't distinguish very much in high frequency, whether that is sound or in this case light. And so this manifests itself on the matrix shown on the left. Actually, no, the matrix shown on the right. And so the matrix here shown on the right shows all the DCT, or the quantization coefficients, and the higher frequency components are on the bottom right, and the smaller coefficients are on the top left. And if you'll see, the smaller frequency components have smaller quantization coefficients, because we need to see a lot of variability in those small frequencies. But at high frequencies where we can't distinguish a lot, we can afford to round the values a lot. We can round them to the closest 100 as opposed to, let's just say, the closest 10, because we can't distinguish at high frequencies. The second pattern that is exploited is that humans cannot detect changes diagonally as well as we can detect changes horizontally and vertically. And so here the matrix on the left shows the common zigzag scanning of JPEG compression. And so we can see here that the values show the indices of the frequency components of the DCT. And so instead of sorting all the DCT coefficients from left to right, top to bottom, we have them in the zigzag fashion, such that jumps diagonally are large, but jumps vertically and horizontally are small. And so this allows us as humans to not distinguish changes as much, preserving the quality of the image without necessarily having to add more bandwidth. And so now, after the quantization and zigzag, we go to the first coding scheme, which is error-resilient arithmetic coding. And so we discussed arithmetic coding in class, and although its compression ratio and its compression efficiency is really great, it is very, very prone and sensitive to transmission errors. One simple bit flip very early on can change the probability by several orders of orders of 2 of magnitude, and that can lead to a very different result at the end. And so a popular scheme of addressing this is discussed here and shown below. Essentially, if during each encoding step an area of the probability, so this entire, you can think about it as the top row here represents probabilities, so it spans a region of 1, and this first block is one message, one simple code word, and it preserves a certain amount of the probability. The 0 is another one in the alphabet, it takes up a certain probability. If we introduce a certain forbidden symbol during each encoding step, then if there is a bit flip at some point in the channel, then there's a likelihood that the bit flip will change the probability such that then the probability lands in one of these forbidden symbol areas. And if that is the case, then at the decoder will try to add this forbidden symbol to the data. It'll realize it's a forbidden symbol, and so therefore it realizes an error has been detected. And at that point, it will try to go back in the bit stream, change certain bits, and then essentially re-decode that bit stream, and it'll kind of repeat until it no longer lands in a forbidden symbol area. Now, after the error-resilient arithmetic coding, you have variable length code words. And so the problem with that is with variable length bit streams, you must now retain the length of each separate bit stream, and those can also be susceptible to loss over a noisy channel. And if that gets lost, then it doesn't even matter that you have very good error resilience in the arithmetic coding. It doesn't know where its particular code word starts or ends. And so to address this, what ERC does is it essentially kind of makes sure that every variable length is assigned into a specific slot such that all of these slots are the same length and that the boundary information is more well known. Now, the boundary information, you may look at this and say, well, you still need to know exactly where every original bit stream that was variable length, information needs to be transmitted to let it know where it actually ends. And you're correct, it does. But the thing is, if this gets corrupted, the most important information usually in an ERAC encoded stream is at the very beginning. Because if the very later bits become corrupted, there's not that much of a change in the probability, and so therefore the decoded symbol will still look kind of similar if it's not the exact same. And so in this case, the decoder, even if it loses information on where, let's just say, this dark green bit stream ends, if it assumes it ends over here, yes, it lost these parts over here, but these are the high frequency components which aren't as impactful. And now the research paper did make sure to mention that N and T need to be sent in a kind of very protected scheme on the side, separate from the transmission of the rest of the data. And so we'll assume that the decoder already knows N and T definitely, and that those are not corrupted. And now the last step is the low density parity check. This is just another, error tolerance scheme. Essentially, LDPC is a way of mapping your message bits to even more message bits, and such that even if there are some bit flips, that message still gets mapped back to your original message. And so an example is like the Hamming code. It's a parity check code. They're like the 7.4 Hamming code that we looked at in class has 4 parity bits. But the Hamming code isn't exactly low density. The difference between N and K isn't as much. Low density parity codes have even a bigger difference. And so now at this point, we've basically looked at all the separate steps in the research paper's proposed scheme. One thing though, the research paper did not mention a lot of numbers. So they mentioned that for the ERAC, the forbidden range was going to have a probability of 10%, and that after they did all the quantization and DCT, they were able to compress the image, which you'll see later on, into 16 bits per pixel. But a lot of other metrics were not included, and so there was quite some flexibility in the way I decided to implement it. However, despite that, here's the picture of my implementation. As you'll see, it's quite different, and one of the main reasons is there were a lot of difficulties with me implementing, so I tried to make sure to focus on the main components. So for example, the first difference, the encoding, there is no EREC or LDPC encoder. So the reason for the lack of an EREC component was that I realized working on the implementation, the separate bit streams were not very variable length. They were almost all the same length, there's maybe only like 1 or 2 bits different. And so instead of sending a lot of information indicating where each separate bit stream ended and assigning them into fixed length slots, I decided it was easier and probably less bandwidth to simply pad those extra bit streams with zeros at the end, because that doesn't affect the probability. And so it essentially makes sure they're all fixed slots, but they are no longer, the boundary information does not need to be transmitted. And so as a result, at the decoder, there is no need for an ECE. And there's no really reverse process for zero padding necessary either. And so the second main difference is the lack of an LDPC encoder or decoder. And with that kind of no longer needed, there's also no longer a cycle between the ERAC decoder and the LDPC decoder. I just realized I forgot to mention that all of these schemes here, the ERAC, the quantization, the zigzag scanning, the DCT, they're all taken over an 8x8 block. That's just kind of standard. So essentially the image, no matter how many pixels it is, if it's greater than 8x8, then we split it up into blocks of size 8x8, and then we perform the DCT, the quantization, the scanning in this way. The ERAC is taken over each 8x8 block. Then the EREC, sorts each of those variable length bit streams that comes from the 8x8 blocks, and so on and so forth. I just wanted to make sure to clarify that. And so now for the results. So I will say, as mentioned earlier, was having difficulty implementing. I'm hoping to still be able to resolve this, but I've essentially reached a problem where on MATLAB, although the error resilient arithmetic decoding and encoding they work perfectly, a signal that is encoded with the ERAC and then immediately then decoded without any noise, without anything, does not generate the image back again. And this is not due to any DCT or quantization or anything. This is simply due to the fact that the probabilities, as I said, the ERAC is done on each 8x8 block, so it's like 64 separate probabilities that are all kind of being jointly combined. So there's slight trouble with like the double precision on MATLAB. So even though the math is right, it gets to a point where the result from the encoder may be slightly more or slightly less than the actual probability that it needs to be. And so then as a result, when the image comes through to the decoder, because the probability is slightly more or slightly less, the decoder tries to assign a value that's slightly higher or slightly lower than the value that it actually should be, in which case a lot of times it might end up assigning the forbidden symbol. And so then, since it's the forbidden symbol, the decoder will detect an error. It'll go back, it'll try to change the bits in the bit stream because it thinks that there's an error. And so it's hoping that by changing the bits that the image might turn out better. It might reach a non-forbidden symbol. But the problem is the current bit stream is the closest it possibly can be to the right answer, because it is the right answer. Or it came from the right answer. And doing a bit flip won't change that. And so as a result, you can see here, the original image is this kind of widely used Lena image. It's 144 by 176 pixels, shown up here in the top left. And so this is with no noise. The research paper gets the image right back. I, on the other hand, am getting this kind of disconfigured image. And so then with a 4% bit flip error across the noisy channel, the research paper implementation gets this image here in the middle on the top row. As you can see, there's quite a bit, there's some disconfiguration, but it's still discernible that it's a person. On the other hand, my image on the bottom, it is slightly different from the one on the left, but not by much. And then once the bit flip error across the channel has been increased to 10%, the research paper implementation at this point has more error, but it's still, visually way better than my implementation below it. The research paper also draws comparisons between its scheme and similar JSCC scheme. There are images for those as well. However, since I didn't explore those other schemes or really mention them, I decided not to include those images here on these slides. And so I know that right now I'm not being able to generate great results. I still do hope to work on this more, and if I generate better results, I will certainly include those in the research paper, or that I the written portion that I submit. But otherwise, this is where I stand now, and this is the research paper that I've been referencing and that I'm basing my implementation on. Thank you for listening. I really do hope that this implementation eventually works. But yes, thank you for listening. Have a great day.